This video looks at linear transformations. Now, before starting, I thought it was a good idea to look at the difference between translations, which we've just done, and transformations. Now, translations have the effect of moving the pre-image to a different part of the plane, but the associated image retains its original size, shape, and orientation. So you are simply moving. And we're doing matrix addition in order to translate. So mathematically, a translation is a simple addition of scalars to the x and y values of a pre-image. So our image of x is our original x plus some scalar a, and our image of y is the original y plus some scalar b. So our translation matrix is AB. In contrast, transformations, a linear transformation has the potential to twist, stretch, and warp the Cartesian plane. So it's not just moving, it's changing shape. It can rotate, it can make it bigger, it can make it smaller. So any transformation that can be represented by a 2 by 2 matrix, such as A, B, C, D, is called a linear transformation. So mathematically, a linear transformation is defined as the mapping of the form where our image of x is equal to ax plus by, and our image of y is equal to cx plus dy. So if we think about this in matrix terms, our matrix that we're transforming with is A, B, C, D, and it is being multiplied by X, Y. So because we go across the row and down the column, you're ending up with the AX plus BY and the CX plus DY. And that's all I've put in this blue box down the bottom. So therefore, a linear transformation can be formed using matrix multiplication. So translations are additions, transformations are multiplication. And our transformation matrix is A, B, C, D. So that 2 by 2 matrix because we have X and Y. So let's look at an example. Determine which of the following are linear transformations. For the transformations that are linear, determine the transformation matrix L. So for this first one, our general form for a linear transformation is that our image of x is going to be ax plus by, and our image of y is going to be equal to cx plus dy. So therefore, this is linear because a is equal to 2, b is equal to 1, c is equal to 5, and d is equal to -1. So looking at it in terms of matrices, our image of x and image of y is our 2x plus y, our 5x minus y. And if it helps, you can put the 1y in front. So our matrix is 2, 1, 5, -1 times by my x and y. So therefore, L is equal to 2, 1, 5, -1. In the next one here, again, our general form, image of x is ax plus by, image of y is cx plus dy. So therefore, it is linear. Our a is equal to 0, our b is equal to 1, our c is equal to 2, and our d is equal to 0. So putting it in matrix form, we have 0x plus y and 2x plus 0y. So matrix is 0, 1, 2, 0. So again, if you want to put that 1 in, times by my x, y. So therefore, my transformation matrix is 0, 1, 2, 0. Now, in the next one, you should see straight off that there's an x squared term. So it's not linear. as the x image includes an x squared. In the next one, you have x plus 4 and y minus 1. This isn't linear. Or this isn't a linear transformation. It's actually a translation. Another example, find the image of point 21 under the transformation with the following rule. So writing it in matrix form. Pull out that translation matrix. So for 2, 1, our image is going to be 3, -5, 2, -4 times by our 2, 1. Cross the row down the column, 3 times by 2 minus 5 times by 1, 2 times by 2 minus 4 times by 1, which is 6 minus 5 is 1, 4 minus 4 is 0. So therefore, the coordinates of the image is 1, 0. Now we can verify algebraically. If we knew that our image was 3x minus 5y and we were doing the 0.21, we can plug that in. So 3 times by 2 minus 5 times by 1, which is 6 minus 5, which is 1. And our y image would be 2x minus 4y, plug in our coordinate, 2 times by 2 minus 4 times by 1, which is 4 minus 4, which is 0. So we know that that's correct. Use the matrix method to determine the image of A after undergoing a linear transformation according to that rule. So write it in matrix form, put it in the right order. So make sure your X comes before your Y. So our matrix of transformation is -2, 1, 1, 3. So for our point A, -4, 3, our image is going to be -2, 1, 1, 3 times by my -4, 3. Cross the row and down the column, -2 times by -4 plus 1 times by 3, 1 times by -4 plus 3 times by 3, -8 plus 3, sorry, +8 plus 3. So -2 times -4 is +8. And then -4 plus 9 is 5. So therefore, therefore, our image is 11, 5. Verify. So it was a point -4, 3. Our original equations plug in. So that's 3 minus 2 lots of -4, which is 3 plus 8, which is 11. And our image for y is going to be -4 plus 3 lots of 3, which is -4 plus 9, which is 5. So that's verified. Now, linear transformations are multiple points. We can do multiple points at the one time. So for the transformation matrix L, A, B, C, D, and the pre-image points A, x1, y1, x2, y2, x3, y3, etc. Our image points can be found by putting our pre-image points in matrix form. So A, B, C, D times by x1, y1, x2, y2, x3, y3, etc., as you can see there. So remembering your coordinates go down. So that's your A, then your B, then your C. That will be your image of A, your image of B, image of C. So let's look at an example. Determine the image of a square ABCD defined by the points, etc. After undergoing a linear transformation defined by the matrix. Sketch the original square ABCD as well as the image. So let's put this in matrix form. Putting our coordinates in a matrix 0, 0, 2, 0, 2, 2, 0, 2. So that's our A, B, C, D. Cross the row and down the column. So you've got 1 times by 0 minus 1 times by 0, 1 times by 2 minus 1 times by 0. Be careful. 1 times by 2 minus 1 times by 2, 1 times by 0 minus 1 times by 2, 0 times by 0 plus 2 times by 0, 0 times by 2 plus 2 times by 0, 0 times by 2 plus 2 times by 2, and 0 times by 0 plus 2 times by 2. You could use your calculator for doing this as well. We all know how easy it is to make a silly mistake. Okay, so therefore, image of A is 0, 0, B is 2, 0, C is 0, 4, and D is negative 2, 4. It asked us to sketch, so our original, we've got A, B, C, and D. So that's our original square. Our transformed 0, 0, so image of A is where A was. 2, 0, image of B stayed the same. 0, 4 is the image of C, and negative 2, 4 is the image of D. So as you can see, we've gone from a square to a parallelogram. So it has actually changed the shape. Now determining the transformation matrix. Given the linear transformation matrix ABCD, the first column AC represents the image of point 1, 0, and the second column BD represents the image of point 0, 0. So looking at this example, a certain linear transformation results in the point A, 1, 0 being mapped to the image 5, negative 1, and the point B, 0, 1 being mapped to the image of B, negative 7, negative 3. Determine the image of the point 2, 5 under the same transformation. So the key is we need to work out what that transformation matrix is. So thinking about this, our transformation matrix is going to be what were they image points. For A, it was 5, negative 1, and for B, it was negative 7, negative 3. So that point's been mapped onto there, and that point has mapped onto there. So our image, or our matrix, is like that. And for the 0.25, It's going to be 5, -7, -1, -3 times by the 2, 5. 5 times by 2 minus 7 times by 5 is -25. -1 times 2 minus 3 times 5 is -7. So therefore, the image point is C, -25, -17.